In the last video, we saw that it was possible for two different elements to end up at the same index of an array. And this was because when we take the ID and we modulus it with the value that we've picked as our modulus operator, there's no real guarantee that the result is going to be unique. There could be two results that are the same as each other. So for these sorts of circumstances, we want to have some sort of strategy to handle these cases if two values end up being the same as a result from a modulus. There's a lot of different ways that we can handle this. The first way that I'm going to show you is an idea known as chaining. With chaining, what we do is instead of having an individual value at each index of our list, we instead have an array at each index of our list. When we have that array, basically what happens is every value that moduluses to that index gets placed into that array. So we essentially end up with a sequence of values that match the ID value modulus that we have given. This allows us to be able to store multiple values at a given slot inside of our hash table, with the cost that we then have to iterate through a second array in order to find our value. Let's take a look at how that's implemented. Basically what ends up changing is this hash table is now going to be an array of values. So basically we're going to have something like this. We're going to have an empty array, and then the way that we could set this up is we could just do a for underscore in range mod, just like this. And that would give us a list of empty arrays matching the modulus value that was provided. So if I give a modulus value 5, there'd be 5 empty arrays inside of my main big list of values, right? And then when we go to insert, basically what we end up doing is we locate this location here, but instead of setting the value, what we're going to do instead is we're going to do an append of that value, because we're going to append it to the list of values that is at this particular location, right? Basically, we're just mapping a list to a particular ID, right? So that's what's going to end up happening here. This still is O of 1. It's technically amortized O of 1 because we're using the append method. However, it's generally going to be O of 1 because we wouldn't expect these lists to get generally like huge or anything like that. So it should be constant time for the most point. In some cases, it may be a bit slower. The get, on the other hand, is going to be a little bit more complicated. So basically what we end up doing is we end up saying, I'm going to keep track of the user that I'm returning, which I'll start off as none. And then I'm going to say for user in self.hashtable at that location. Right, remember, when I do ID modulus self.mod, what I get as a result is a list. So I'm then iterating the list that I'm given. And what I'm going to do is I'm going to search to see if the ID that I'm currently at is equal to the ID that I'm looking for. If it is, that becomes the user that I'm going to return as my value. And then basically at the end here, all I do is I just return ret user as a result. And you'll see that this will generally work, right? So when we take a look at this example here, right, in this case, right, if I take a look at just like the hash table that I actually have, you'll see that all the values still get inserted as expected, but they're just inserted into their own little list. You see that this is now a list of values at 0. This is now a list of values at 1. This is now a list of values at index 3, right? So it still does work generally. Now I'll just show you an example of a collision, right? So if I have a user, say, with a value of 6, we'll just give them some sort of name like this, right? We'll see that this one should result in a collision for us. So let me show you what happens here. So you'll see here now that at slot 1, we have 2 values inside of that list, right? So you can see that it just places it inside of the list of values that match that particular slot in the array, right? So now if I were to try to get those values, right? If I try to get at index 6, I could show you that it will still give me the right user generally. So we could see here, in this case here, did I just miss I just missed the index here, right? So this should be the ID here. I realized that I forgot to give that as an argument. There we go. And then to just verify that this is correct, we could just print out that username property. And you can see that that gives me Jeff, which is the value with ID 6. But if I were to change this to be, say, ID 1, I should get the user that matches that, which is Sarah in this case. So you see that it still gives me the right ID value generally. It's not going to give me something that, doesn't match up to the ID that I'm searching for. It just has to look through an array now in order to get there. So what's the worst case of this? Technically, the worst case of this is on. That would happen if every single value went to the same slot in our hash table. That would be very rare, but it could happen, right? So on is technically our worst case, but most of the time, it's going to be constant time. So this is still better than a linear search, but it does have a problem that sometimes it could be just as bad as a linear search, or it could be, not a great performance overall, right? Now with our contains, we end up with basically the same sort of process as our get, right? Basically, what we're going to do is we're going to say contain equals, I would start it off as false. And then basically what I would say is if the user matches the user ID, then we could just say contain equals true. And then we could just return back contain as a result, right? Same sort of process as this get here. And again, this could be worst case on. It's probably not likely that will happen, but it could be as well. So this approach does work pretty well, right? It gives us that ability to continue to have a pretty good lookup time, a pretty good check for contains. Our insert is still pretty good. The main downfall to this is that we are again having to rely on things like the append method, which have this amortized time complexity, and the built-in data structures require us to use a bit more memory to be able to store our data. So it would be really nice if we didn't have to use an extra data structure to resolve this collision problem. So in the next video, we're going to take a look at something known as open addressing, which is a way that we can actually solve this problem without needing to add another data structure, in this case, a list, to our problem. So thanks so much for watching. I'll see you in the next video.